seeing as it's past noon, it's time we get started. Today, I'm thrilled to roll out the latest episode of the IBM Qiskit Live Quantum Seminar Series dedicated to you, the research and academic communities. I'm your host, Zlatko Minev from IBM Quantum, and today I have the special pleasure of hosting Nicole Halpern, who is a NIST physicist, Quicks Fellow, and adjunct professor, assistant professor of physics at the University of Maryland. Nicole received her doctorate in physics from Caltech in 2018 under John Presko's auspices. Nicole's thesis won the International Ilya Prigogine Prize for Thermodynamics. After that, Nicole continued as an ITAM postdoc fellow at Harvard University until joining NIST in Maryland. Nicole's research has a very catchy and unique name, Quantum Steampunk. And Nicole's written an upcoming book called Quantum Steampunk, The Physics of Yesterday's Tomorrow, which maybe we can ask her about at the end of this presentation. And with that, hello, Nicole. How are you doing today?
I'm doing well, thanks. Thanks for having me here.
It's a pleasure you accepted our invitation. Where are you tuning in from?
I'm tuning in from Maryland.
All right. Well, I can see everyone here is already very active and excited in the chat. So folks, feel free to post questions. And with that, Nicole, the stage is yours.
Great. Thanks very much. And although I can't see the YouTube channel directly, I'm thrilled to be joined with everybody here and looking forward to sharing with you. This talk is called Linear Growth of Quantum Complexity, and complexity is a very loaded term. It has lots of different meanings. For instance, the Kolmogorov complexity is the length of the shortest program required to prepare some desired outputs. Computational complexity, probably a number of us learn about in quantum computer science class. There's a type of complexity that characterizes networks, such as brains and social networks. I've actually also written about that type of complexity with a great PhD student. I'd like to highlight Logan Hilberry, but I'm actually not going to talk about that type of complexity or the other types of complexity. I'm going to talk about something that's kind of vaguely named quantum complexity. As advocated for by a number of quantum physicists, I'm going to focus most on the perspective by Adam Brown and Lenny Susskind. By quantum complexity, I mean a measure of the difficulty of implementing a unitary on some number n of qubits. For instance, in the absence of noise, in order to implement the identity operation, you don't have to do anything. So it has a complexity of 0. According to a counting argument, the maximum possible complexity grows exponentially with the system size. There are many different ways to quantify quantum complexity. One way is the geometric approach introduced by Michael Nielsen and collaborators. They were thinking about having some quantum many-body system evolving under a fixed Hamiltonian that introduces an evolution across some period of time. So the unitary implemented initially is down here, the identity operator, and then as you let time run, the Hamiltonian implements a unitary that traces out some trajectory in the space of unitaries. This space is one on which you can define a metric. You can use that to calculate the distance from the identity operator to the final unitary using differential geometry. Because of that use of differential geometry, this approach is beloved by high-energy theorists. Quantum information theorists love a strategy that I'll call the exact quantum circuit complexity. Let's define as C of U the minimum number of 2-qubit gates needed to affect a desired unitary. These gates don't need to be geometrically local. The exact quantum circuit complexity upper bounds Nielsen's complexity, as we can see from this sketch. So this red curve represents the path traced out by the Hamiltonian that I mentioned in association with the last slide. It's some smooth curve, and so it is shorter than this jagged curve, which represents the evolution implemented by 2-qubit gates, which are discrete and so account for these corners, these jags. Also, the opposite relation between these two measures of complexity holds in an approximation scheme that I'll mention later. quantum complexity has risen to become a very relevant concept in a number of subfields of quantum many-body physics. The one that alerted me to this concept and got me working on it was high energy physics. Even though I'm not exactly a high energy theorist, I only occasionally pretend to be when working on quantum information theory like this problem. There is a correspondence between ADS, anti-de Sitter space, some gravitational background, and a CFT, a conformal field theory, so a quantum theory that lives on the boundary of this space. In this ADS space, there can be two black holes connected by a wormhole, and one can show that this wormhole's length will grow linearly in time for an exponentially long time. One can ask, what is the dual in the CFT, the conformal field theory, of this wormhole? In the conformal field theory, well, the conformal theory has some quantum state. One can measure local observables and even measure kind of odd correlation functions that signal quantum information scrambling, but these quantities reach their equilibrium values much more quickly than this wormhole length does. The wormhole growth paradox is supposedly there is a duality between these two pictures, but there's a quantity here that grows in a particular way, and this quantity doesn't seem to have a dual in this picture. A resolution was proposed in the complexity equals volume conjecture. According to this, the quantity dual to the wormhole's volume is the complexity of this conformal field theory state. And after the complexity equals volume conjecture was proposed, complexity was conjectured to be dual to other things, the action, a particular action in this picture, and I even recently saw a paper called complexity equals anything. So that's the relevance of quantum complexity to high energy theory. Complexity has also been appearing in other subfields of quantum many-body physics. For instance, quantum computation, in which the task of quantum advantage or supremacy is relevant. Sorry about the reference in this crowd. Maybe I shouldn't have used that. But we're all interested in using quantum computers to achieve something that isn't easily achievable with classical computers. And one can do that if one's quantum computer prepares a state that is sufficiently complex that it's very difficult to simulate with a classical computer. So in condensed matter, we can have some Hamiltonian that has a gap, and that Hamiltonian can be in a non-trivial topological phase, just if the ground state has a decent complexity. So a complexity that's greater than a constant in the system size. So this idea of quantum complexity is making the rounds of quantum physics. Adam Brown and Lenny Susskind in 2018, although originally their paper came out in 2017, laid out two conjectures about quantum complexity that have become quite prominent. So first is Mary, quite contrary. How does your complexity grow? There's a conjecture that under generic chaotic evolutions, the quantum complexity grows linearly in time for a time that's exponentially larger than the system size. So this is roughly linear, and this time scale is exponential in the system size. Second, yes.
Quick, very, very crude, intuitive question. Can you think of this as somehow equivalent to kind of diffusive, the radius of your diffusion grows linearly as opposed to in ballistic transport where things go quadratically, where when you have coherent propagation? Is that maybe potentially an analogy one can draw?
So at early times, the linear growth of complexity, I think we can reason about to some extent by thinking of more familiar quantities like entanglement. So at early times, I think entanglement has been shown to grow linearly, and in this regime, to make entanglement grow linearly, you have to apply a number of circuits that grows linearly. So that's one reason to expect the complexity to grow linearly at early times. As the time becomes exponentially long, then it's much more difficult to latch on to another phenomenon that's familiar and well known from quantum many-body physics and quantum thermalization for reasons that I'll discuss later.
Awesome. Thanks, Nicole.
There's also this conjecture that one can define a resource theory for uncomplexity that involves a couple of pieces of jargon, so let's break those down. By uncomplexity, or to explicate uncomplexity, we need to start with the complexity of a state. So we talked about the difficulty of applying a unitary. So similarly, we can think about the very closely related concept of the difficulty of preparing a desired state from a simple tensor product. We can define uncomplexity as the maximum possible complexity of any such state minus the actual complexity. So this gap is useful. How come? Because people listening to this talk are building quantum computers. What do we put into a quantum computer? A simple tensor product. It serves as scrap paper that the quantum computer uses to write calculations on. So uncomplexity is useful for quantum computation, and closeness to the simple tensor product is useful. We could say that it's a resource. A resource theory is a simple model developed in quantum information theory for any situation in which the operations we can perform and the systems we access are constrained. So this is a great review. The field of resource theories has burgeoned over the past few years, and one of my home bases is resource theory, the resource theory framework. We use resource theories to formalize operational tasks like the distillation of high quality entanglement from lower quality entanglement, and to calculate the optimal efficiencies with which we can perform those tasks. So we might want to define a resource theory for quantum uncomplexity. So those were two conjectures laid out in that paper. Now, a number of papers have referenced that paper and have provided evidence for these conjectures, although there has been also a broader literature for a few years about these conjectures, especially the linear growth one that has been worked on for a number of years. And I've had the wonderful privilege and pleasure of working with a great team on presenting proofs of those two conjectures. So Jonas Haferkamp, Philippe Feist, and Teja Kothakunda have been working in Jens Eisert's group in Berlin, and Anthony Munson is in my group in Maryland. So this paper at the top contains the proof of the linear growth of complexity conjecture, and this paper down here contains the definition of the resource theory for uncomplexity, and we use results from up here to prove statements about this resource theory. I'm going to focus on this top paper. So here's where I'd like to go in the rest of this talk. First, we'll talk about why this problem is hard, why you have to write a whole paper about it. I'll establish the setup, then introduce some terminology and a mindset for approaching this problem. I'll state the main theorem and then sketch the proof, then talk about opportunities for future work. Lower bounding the growth of quantum complexity under typical random dynamics for an exponentially long time is a tough problem. It's been worked on for a number of years by a lot of really smart people whom I really respect. They've been able to prove statements about certain regions of the problem space. For instance, one can, as I discussed earlier briefly, focus on short times and prove some statements about that, or imagine that our system consists not of qubits, but of very high dimensional systems. People have used the mathematical toolkit of unitary T designs, which approximates totally uniform randomness. And often one assumes that there's a lack of collisions in the following sense. Here's why it's really difficult to lower bound the quantum complexity. If we're running a circuit, that's our model of the dynamics, then gates performed later can cancel gates performed earlier. And so the complexity might actually decrease over some time scale. For instance, if we're running a circuit, we could perform a C0 gate to entangle these two gates, and then we could perform another C0 gate, which will undo this one. And so the minimum number of gates you need to prepare your state from here to here increases, and from here to here increases, but from here to here decreases. We say that these two gates collide. So often people will just assume that collisions almost never happen in order to use the conjecture of linear growth and move forward using it. It's difficult to prove that collisions almost never happen, even though we believe strongly that they probably never happen, or the community has believed that strongly for a few years. But it is worth trying to prove. Since we're quantum information scientists, we try to do things rigorously. Here's the setup that I'd like to keep in mind. We'll think about a system of n qubits. I'm going to assume for convenience that n is even. We'll imagine these qubits undergoing a circuit of two-qubit gates chosen from SU4. And these gates are chosen Haar-randomly. The Haar-randomness, loosely speaking, means chosen uniformly randomly. The Haar measure is the unique unitarily invariant measure on this group. Again, these gates don't need to be geometrically local, but they can be if you want for them to be. This model captures some features of chaos. So that's one reason why random unitary circuits have been very widely used in quantum computation and condensed matter over the past several years to learn about quantum many-body thermalization. I'll denote the z component of the spin like this so that the zero state, or the +1 eigenstate, is denoted by 0. And I'll sometimes denote tensor products in this way. In our paper, we introduce some terminology and a mindset that really came out of Jonas's work. So he did a kind of amazing job of approaching this problem of linear growth in a way that is totally different from how people approached it in the past. Let's say that an architecture, A, is the way that you lay out a fixed number of gates in a circuit, or the way that you lay out a fixed number of gates. Let's call that number R. A popular example is a brickwork architecture. So in the first layer here, a gate acts on qubits 1 and 2, a gate acts on qubits 3 and 4, and so on. In the next layer, a gate acts on qubits 2 and 3, a gate acts on qubits 4 and 5, and so on, and then this coupling pattern repeats. If you take an architecture and you choose particular gates to put into it, then you get a circuit. If you take the circuits and you contract it along these lines representing qubits, then you get a unitary in SU2 to the n. This contraction is implemented by a map F that depends on the architecture A. Suppose that you put two vertical cuts into this circuit. The gates in between the cuts we'll call a block. And a block can contain a backward light cone, which we define as follows. So, suppose that there is some qubit T that connects via some path of gates to each other qubit, and that path might be unique to each other qubit. Then we'll say that this block contains a backward light cone.
Nicole, maybe just a little bit of a question on the motivation for the particular choice. Could you say a little more about that, and how important is of the architecture and how of the brickwork, and how important are things like well, I mean, we're sort of at a more abstract level, but if I had to think about the physical limitations and connectivity of the qubits and so forth.
Yeah, the brickwork doesn't matter. It's just an example that I'm using because people are used to seeing brickwork circuits. They're very popular. And so it's an example of a circuit that contains backward light cones. And so I'll use it to illustrate what a backward light cone looks like. But in the theorem, all we're going to need in a backward light cone, just if a circuit has backward light cones, that means that the circuit is well connected, and that this qubit connects to all of the qubits, all of the other qubits. So there's this sort of good connectivity within the circuit. And that property is the only property that we're going to need in our theorem. So I'll illustrate the theorem again with a brickwork circuit because it's easy to draw and it's familiar, but we just need this backward light cone property. And it turns out that circuits that contain backward light cones are extremely common. And even if you just write down a random circuit, it will probably contain backward light cones. I can talk more about that later.
Thank you.
Sure. But for example, this qubit connects to this qubit via a path of gates because this qubit down here enters this gate and so connects to this qubit, which enters this gate and so connects to this qubit, and so on and so forth until this bottom qubit connects to the top qubit. And again, the path connecting this qubit to each of the other qubits might be unique to those other qubits. The gates that form these paths form what we call a backward light cone. And as I just said, if a block of gates contains a backward light cone, then the block is well connected in a sense. Here's the main results, the theorem about the linear growth of complexity. Let's say that A is any architecture that we can form by taking T blocks, each containing at most L gates, and concatenating the blocks, putting them one after the other. Also, each of these blocks we'll assume contains a backward light cone. So in a very simple example, we can imagine having a block formed from a brickwork circuit. Let's say that the minimum number of gates in this block is L. And we can imagine having T copies of this block in a very simple example. Again, we're denoting the total number of gates by R. Suppose that we have this architecture and we slot in some gates, then we implement a unitary U. So consider any unitary that we can implement with a circuit in this architecture. For any such unitary, the exact circuit complexity obeys this bound. The bound's key feature is that it depends on R, the total number of gates, linearly. And the total number of gates grows as time grows, as the circuit grows longer and longer. So this lower bound on the circuit complexity depends linearly on the time as we wanted. So more specifically, the lower bound has the form of the total number of gates divided by 9 times the maximum number of gates per block minus the number of qubits over 3. And this bound holds for all t. Remember, t is the number of blocks, so it's also a measure of time. For all times up to those exponentially large in the system size. And that's exactly what we were hoping to prove. This minus n over 3 doesn't really matter because, again, what's really difficult to prove is this bound in the exponentially long time regime. And at exponentially long times, this total number of gates, which is a measure of time, is exponentially large. And so this linear term is nothing in comparison. The key idea behind the proof is a quantity that we call the accessible dimension of an architecture. Here again is a simple example of an architecture. We said that if we slot gates into the architecture and then apply this contraction map FA, then we get a unitary. Now, consider the set of all such unitaries that we can implement using this architecture by slotting in different gates. The set of all such unitaries is the image of this contraction map. The accessible dimension of the architecture is, loosely speaking, the number of degrees of freedom that we need to describe this set of all unitaries implementable. So to be more precise, I'll need to introduce some algebraic geometry, very basic algebraic geometry that you can find more information about here, but we only need a few points from it. And this algebraic geometry toolkit is quite different from the toolkits that have been applied to studying complexity, quantum complexity in the past, such as Michael Nielsen's geometry and unitary T designs that I mentioned earlier. Suppose that you have a set of equations. It has a set of solutions. That set of solutions we call an algebraic set. One example of an algebraic set is SU4 times R. So this consists of all of the sets of R two-qubit gates. And why is this a set of solutions to equations? Because the special unitary operators satisfy these equations. So the unitary operators in SU4 are unitary, number 1, and number 2, they are in the special unitary group. Every algebraic set is a semi-algebraic set, which is more general. Suppose that you have a set of equations and perhaps inequalities. The set of solutions to these is a semi-algebraic set. A useful result in algebraic geometry is the Tarski-Seidenberg principle. Suppose that you have some semi-algebraic set, W, and you have a map, a polynomial map, F, from real numbers to real numbers. So if you take that map and you act it on your semi-algebraic set, then you get another semi-algebraic set. So in our case, the initial semi-algebraic set of interest is going to be SU4 times R, which again consists of the sets of R two-qubit gates, which we might be slotting into our circuit. This function of interest is going to be our contraction map that we use to take a circuit and turn it into a unitary. This function, just for anyone who is concerned, is a polynomial function because it multiplies matrix elements together. And the result of taking this contraction map and acting it on a set of R two-qubit gates will give us the set of all possible unitaries implementable with that architecture A. Another result in this mathematical toolkit is that every semi-algebraic set can be expressed as a union of manifolds. And one of those manifolds has the greatest dimension. That dimension is the dimension of the whole semi-algebraic set. We said that U of A, this set of all unitaries implementable with our architecture, is a semi-algebraic set. So it has a dimension. And that dimension is the accessible dimension of our architecture. But if all of this is too much detail, then just think of the accessible dimension as the number of degrees of freedom that we need to describe this set of all unitaries implementable with the architecture. Any questions?
I guess by that essentially you mean number of parameters.
Yeah.
Go on, thank you.
Okay. We will use this accessible dimension because we're going to use these toolkits of algebraic geometry and differential topology to learn about the accessible dimension, which is a part of those toolkits. And once we learn about the accessible dimension, we can infer about a unitary's quantum complexity. But here's a sketch of the proof. There are many levels of detail behind the proof, so if you want to know more about them, then feel free to ask during the question and answer session, although there's a lot of detail that can be said. So the most difficult part of the proof is to lower bound the accessible dimension of an architecture A. The lower bound is the number of blocks in our circuit. Some key elements of the proof include these toolkits of algebraic geometry and differential topology. And we also construct a particular Clifford circuit. A Clifford unitary transforms the Pauli operators to the Pauli operators within some phases. Let's say that an n-qubit Pauli string is a tensor product of single qubit Pauli operators and single qubit identity operators. So if you have any n-qubit Pauli string, as long as it's not trivial, it's not just identity operators, you can turn it into a Pauli operator that acts non-trivially on only one qubit, only, let's say, the nth qubit, and let's say we choose for it to act on the nth qubit as a z. We can transform one string into the other via some Clifford circuit. Now, these n-qubit Pauli strings form a basis for the whole space of n-qubit Hermitian operators. And the number of non-trivial n-qubit Pauli strings is 4 to the n minus 1. That ultimately is why our bound on the quantum complexity holds for a time up to 4 to the n minus 1. So first we prove a lower bound on the accessible dimension, then we prove an upper bound on the accessible dimension. This bound is 9 times the total number of gates in the circuit plus 3 times the number of qubits. The proof of this bound is not as difficult, although it still requires some thought. It's a parameter counting argument. And you can also feel free to ask about that later. So we can put everything together as follows. Let's recall the assumptions in the theorem. We said that A is some architecture, some arrangement of gates, such that the architecture contains T blocks. Each block contains a backward light cone, and each block contains at most L gates. The total number of gates, we said, is called R, and that's upper bounded by the number of blocks times the maximum number of gates per block. If you have this architecture, you can slot in different gates and with many different choices, and so you can implement lots of different unitaries. The set of all unitaries implementable with this architecture is U of A. Suppose that we randomly pluck a unitary from this set, U of A. We would like to know with what probability can you implement U with a shorter circuit, with a circuit whose total number of gates, R prime, is less than the actual total number of gates that we were considering in our original architecture over 9 times the total number of gates per block minus the number of qubits over 3. In other words, with what probability can this random unitary, does this random unitary have a complexity that violates our lower bound? Well, I said that the theorem is true, so the answer to this question has to be probability 0. So with probability 0, the unitary violates our bound. And we can prove that statement using the lemma that we just discussed. We said that we're imagining, is it possible to implement this unitary with a relatively short circuit, with only R prime gates, that obeys this inequality? Now, R over L is T, the number of blocks in the circuit. Let's make that substitution, and then let's reorganize this inequality to solve for T, the number of blocks in the circuit. The number of blocks is greater than 9 times the small number of gates plus 3 times the number of qubits. Back at the beginning of our proof sketch, we proved a lower bound on the accessible dimension. The accessible dimension is at least the number of blocks, so we can chain these two inequalities together. So the accessible dimension of the original architecture we had in mind is greater than 9 times the lesser number of gates plus 3 times the number of qubits. Now, we're imagining, or we're asking, is it possible to implement this unitary with this lesser number of gates R prime arranged in any architecture, A prime? So consider any architecture A prime of this lesser number of gates. We can upper bound its accessible dimension because we proved another bound on the accessible dimension back near the beginning of our proof sketch. We said that the accessible dimension is upper bounded by 9 times the number of gates plus 3 times the number of qubits. And we can chain these inequalities together. In conclusion, the accessible dimension of this smaller architecture is strictly less than the accessible dimension of this larger architecture. That's a really important inequality, so I'm going to rewrite it. It implies, well, we can put it together with this lemma that we also proved. So consider all the unitaries that you could implement with this little architecture. If this inequality holds, so the little architecture has a lower accessible dimension than the full architecture, then all of the unitaries you could implement with the little architecture form just a measure zero subset of all the unitaries you could perform with the big architecture. To prove this lemma, we use the dimension theory of real algebraic sets. So if you randomly pick a unitary implementable with the larger architecture of R gates, then because of this measure zero statement, your probability of being able to implement that unitary with a smaller circuit is 0, which is exactly what we wanted to prove. Does anybody have questions about that?
Raphael had a broader question, and maybe we'll touch on this later, but how does the result of complexity relate to, for instance, ideas from thermodynamics, maybe from the resource theory point of view? It's a little bit. Yeah.
We could, it could make sense to touch on that. Oh, yeah, there's a slide that's relevant to that. So we could have more of a discussion about that when that comes up.
Okay.
And let me know if what I say then isn't sufficient and you want to know more.
Yeah, stay tuned, Raphael.
Anything else?
Yeah, well, maybe if you could just try to summarize for us again the you know, how to think sort of succinctly about why t should be less than 4n minus 1. You know, 4n minus 1 being sort of the number of non-trivial polystring elements. You know, why does that sort of bound the number of blocks that you need at a high level?
Yeah, so the proof depends on
I guess I mean more in terms of like the motivation or intuition. If there is an easy one, go ahead.
So we started off by talking about quantum complexity, and then we shifted to talking about a quantity that's easier to reason about using algebraic geometry, which is this accessible dimension of circuits. And you can actually shift the argument further to talk about something that's even easier to reason about using this mathematical toolkit. And so that final mathematical quantity, we can bound how it grows. We can reason about how it grows. And we can do that by constructing just a circuit and reasoning about how that circuit can, okay, well, actually, it might take me a moment to come to a good formulation of an answer to this question, because there are sort of concepts piled atop of concepts, because as I said, how many layers of details there are in the proof. So how about we come back to that in the end?
Back to that. That sounds good. Yeah, that's good. That sounds good. Great. And maybe final question from the audience: can you remind us if or what constraints there are on any of the unitary? Apply for any unitary? Does this theorem apply for any unitary, or what are the constraints again?
So the assumptions in the theorem are that we have n qubits. The statement we are thinking about an architecture that consists of T blocks. Each block contains at most L gates, and each block contains a backward light cone. So this is an architecture, and with this architecture, you can implement a whole bunch of different unitaries. So if you pick any unitary from that set that's implementable with this architecture that has these properties, the theorem applies. You can the complexity of this unitary obeys this linear lower bound with a probability of 1.
Good. Thank you.
Sure.
All right.
This result has an implication for this wormhole growth paradox if we want to return to thinking about the complexity equals volume conjecture. We said that the volume of a wormhole grows linearly in time for an exponentially long time, and we managed to show that the quantum complexity of pure states under a pretty generic random evolution also grows linearly in time for an exponentially long time. And that result suggests that, or it indicates that we have more evidence to think of the wormhole volume and the quantum complexity as possibly dual to each other, or so the quantum complexity and any of these other things that grow linearly in time for an exponentially long time in the anti-de Sitter space. We can extend this result in a number of ways. We've been talking about the difficulty of implementing a unitary and unitary complexity, but we can also lower bound the exact state complexity that we talked about all the way at the beginning of the talk. Consider any n-qubit pure state psi. Let's call C sub s of psi the least number of 2-qubit gates that we need to prepare the state from a simple tensor product. We can prepare the state from a simple tensor product using some unitary. And if that unitary satisfies our theorem's assumptions, then the state complexity obeys the exact same linear lower bound, also for an exponentially long time. This exponential is a little bit different than the exponential in our unitary theorem because the space of states differs from the space of unitaries, but the scaling is still exponential. And this result we applied in our resource theory in a way that I'll mention later. We can also consider a random architecture, as I mentioned briefly in response to a much earlier question. So we can take our theorem, look at the assumptions in it, and remove the assumption that each of our blocks in our architecture contains a backward light cone. If we loosen the restrictions on the setup, we remove an assumption, then we pay a little price of getting, instead of a lower bound that's obeyed with probability 1, a probabilistic lower bound on the exact circuit complexity. In an example of constructing such a random architecture, we can imagine that at each time we randomly pick 2 nearest neighbor qubits in addition to randomly picking the gate applied to those qubits. For instance, at this time step, we could pick these 2 qubits, and then these, and so on. It turns out that the gates automatically form backward light cones all by themselves with high probability. And so with high probability, the complexity obeys a linear lower bound. So here's the form of the bound. So here's the probability that the complexity of the unitary that's actually implemented obeys some lower bound. And this lower bound, very importantly, depends linearly on R, the total number of gates, and so a measure of the time. So again, we have a lower bound on the complexity that grows linearly in time. The probability that the complexity obeys this linear lower bound is pretty high. It's 1 minus some correction. Actually, this is a whole family of bounds because there is this parameter alpha in the statement of the bound. So alpha is any number you please between 0 and 1. For example, suppose that alpha is large, then, well, if alpha were small, it would suppress this lower bound so that the lower bound would become near trivial, near 0, and of course the complexity is at least 0. But if alpha is high, then the complexity is lower bounded by a significant number. So if alpha is large, then this lower bound is not suppressed, and it becomes more probable that the lower bound is violated. Because if alpha is large, then 1 minus alpha is really small. So this denominator is small, so this whole fraction is large, and it has a decent chance of canceling out this 1, so that the probability could be close to 0. So again, this is a whole family of bounds. And as some people might guess from the form of this inequality, a key tool in the proof is Chebyshev's inequality. we can also try to lower bound the approximate circuit complexity. So what do we mean by that? Suppose that you're interested in some unitary that satisfies the assumptions in our theorem. You can imagine trying to approximate this unitary with another unitary, a u prime, that you can implement with a short circuit, one that violates our bound on complexity. Then you can prove that with high probability, this approximation is actually not a good approximation. It has a large Frobenius distance from the desired unitary. So for all values of some parameter delta, there exists an epsilon such that with high probability, the Frobenius norm between the desired unitary and the approximation is large, at least epsilon. Unfortunately, this epsilon can be uncontrollably small, so it's possible that this epsilon could be really, really, really near zero, in which case this statement is trivial. It would be basically that the distance between these unitaries is at least zero, and of course it is. The distance between any two unitaries is at least zero, so that isn't terribly interesting a statement. It is a shortcoming of our attempt to extend our result to approximate circuit complexity. Here's why there's the flaw in that extension. So we are saying, suppose that you want to implement U, but in some family, U of A of unitaries implementable with the architecture A, but what you actually implement is some U prime in a family of approximations, U of A prime. We're allowing approximations, and that means if you implement any of these unitaries in the second set, well, we'll consider it as though you implemented something nearby. That's what we mean by an approximation. So we take this set U of A prime and expand it to effectively include all the unitaries close to that set in some matrix norm. And so the set grows in all directions in the space of n-qubit unitaries. As a result, this accessible dimension, this really important tool in our proof, goes all the way up to its maximum value. So it's not the accessible dimension is not a sensitive enough measure that it'll increase just a little when we try to increase the set of unitaries just a little to allow for a little approximation. So if the accessible dimension of the approximation leaps to its maximum possible value, then this extremely important inequality that I wrote twice in our proof is probably not satisfied. So it looks like the accessible dimension is maybe on its own is too crude a tool for extending our lower bound from exact circuit complexity to approximate circuit complexity. But I can talk a little more about that later. Finally, someone asked about the resource theory of uncomplexity. We did use the results in this first paper about the linear growth of complexity to prove statements about monotones in the resource theory of uncomplexity. So a monotone is a concept in the framework of resource theories. A monotone is a function that you evaluate on a state, and it's a measure of how much value, how much resourcefulness the state has. And if you take this state and you apply to it some of those operations that are easy to perform, that are allowed by the constraints in your resource theory, then the value in that state will tend to decrease monotonically, the way that in thermodynamics, if you start with some maybe non-equilibrium state, like a compressed gas that can perform work, and you allow it to thermalize, so you let the gas expand across its container, then the thermodynamic system's free energy, and so its capacity to perform work decreases monotonically. And so the resourcefulness, that ability to perform work, decreases monotonically during thermalization. So monotones are similar in resource theories generally. So we used the linear growth proof to prove the existence of some monotones in our resource theory for uncomplexity. These extensions lead into opportunities for future work. As I mentioned before, it would be, well, what I said before suggests that it would be nice to strongly lower bound the approximate circuit complexity to go beyond the approximate circuit complexity bound that we were able to get. It seems, again, that we might need to move beyond this useful tool of the accessible dimension that enable us to crack the problem of the exact circuit complexity, but we might need some more fine-grained thinking about, say, sort of the arrangement and geometry of these different groups of unitaries in the whole space of unitaries. So the set of the unitaries that you really want to implement and the set of unitaries that approximates that. If you can prove a strong lower bound on the approximate circuit complexity, then you can lower bound this other measure of complexity that high energy theorists like, Michael-Nielsen's complexity. Because you can show that Nielsen's complexity upper bounds the approximate circuit complexity, which ideally can be lower bounded in opportunity number 1. So this work showed that this concept of an accessible dimension of an architecture is a useful mathematical tool in many-body quantum physics. Again, it's totally different from the mathematical tools that have been used to reason about quantum complexity until now. And again, I credit my wonderful co-author, Jonas Haferkamp, with formalizing this idea. Until now, people have been appealing to entanglement entropies and differential geometry and T designs. So there are a lot more problems in quantum many-body physics that involve randomness, and it would be interesting to see if some of them could be helped with this interesting tool, like maybe Brownian circuits or hybrid circuits, which have been extremely popular recently. There are also a number of opportunities opened up by the definition of a resource theory of uncomplexity that I could talk about later if anyone is interested. In summary, we saw that quantum complexity is a concept that is useful across quantum many-body physics. Adam Brown and Lenny Susskind in 2017 put forth, or let's say formulated, 2 conjectures that have been bouncing around the literature and talks for a few years. First, Mary, quite contrary, how does your complexity grow under some random typical dynamics? We would guess linearly in time for an exponentially long time. Second, there's the conjecture that we can define a useful resource theory for quantum uncomplexity. We managed to prove these conjectures. We talked about one of the proofs in some detail. It relies on the toolkits of algebraic geometry and differential topology, and especially this concept of an accessible dimension of an architecture. There are lots of opportunities for future work. Thanks very much for your time.
Thank you very much, Nicole, for the very nice and detailed talk. Folks, feel free to post any final questions in the chat as we get to the last few minutes of the talk and presentation here. Maybe just on that last slide, Nicole, you briefly mentioned, I think it was under point 3, you briefly mentioned, how some of this machinery is applicable to, random processes and the variety of systems you might have in the many body physics community and hybrid circuits, I think you mentioned. Would you like to just expand a little bit more on where you see some of the intersections here?
So the accessible dimension has, in this case, been proven useful in a context in which we are thinking about a random circuit. And we were able to use this tool in order to prove something about how complexity, this really tricky concept to capture mathematically or reason about, prove things about mathematically, grows under a random circuit. But there are these other models for random circuits, Brownian circuits, hybrid circuits. And to get a hybrid circuit, you take random circuits and add in measurements of the qubits. So these are sort of deformations of the maybe very simple, one might say, random unitary circuit model that we had in mind. So if there are problems in those settings, maybe that need solving, maybe the accessible dimension could be a useful mathematical tool. Or also, I haven't seen quite as much literature. Let's see, I think I haven't seen literature about complexity in the context of hybrid circuits, although I could just be missing something. And so it could well be interesting to, a lot of the results about hybrid circuits have been about, say, entanglement. And I think of there as being multiple stages of quantum many-body thermalization, and the equilibration of the entanglement entropy is a very early stage of equilibration. After that, out of time-ordered correlators reach their saturation values, and then after that, complexity saturates. So if one would maybe move beyond entanglement to thinking about the complexity of something like a state evolving under a hybrid circuit, then perhaps there the accessible dimension might be useful.
Yeah, thank you. And question from the audience on maybe kind of flipping this around on its head and asking, how could this theorem potentially inform the design of quantum circuits? Could we potentially look at it that way?
Yeah, that could be a useful application. Suppose that you would, and this is why a number of people like Aram Harrow and Fernando Brandao have thought about quantum complexity in the context of quantum computation. So we have relatively small scale quantum computers, and we'd like to do with them something that's difficult to do classically. So if you prepare a state that really requires a lot of gates for some meaning of a lot, then it's likely that you can perform some task that is difficult to do classically. And complexity is a measure of how difficult it is to prepare that state, which is linked to how difficult it is to simulate that state classically. So we know that at least there's this class of circuits that that meet our theorem's requirements, that, under which the complexity grows linearly in time for a very long time. And so complexity grows very quickly. So if you're trying to get as much as possible out of your limited quantum computer, then maybe you would want to focus on circuits like this.
I see, and circuits like this would be kind of random and have this light cone structure, and well, I guess one architecture is the brickwick, I think you called it.
Right. So, for instance, maybe you want to learn something about the stages of thermalization in a quantum many-body system, or perform some other task that requires randomness.
Great. Folks, feel free to elaborate on your questions in the chat. Let me read final questions here. I'm not quite sure if I understand this question, but I'll read it to you and then you make of it as you wish. Is there any effect of large numbers of non-commuting unitaries on the accessible dimension of a given architecture?
So I'm thinking maybe suppose that you have some architecture, and it sounds like the asker of the question is imagining that you slot into that architecture. The choices that you make for gates are gates that don't commute with each other. Does that choice have an effect on the dimension of the architecture? So the dimension of the architecture actually depends only on the architecture. It doesn't depend on which gates you choose to slot into it.
I see. As long as, I guess, you have some sort of complete coverage in the sense.
What do you mean by that?
Well, I guess I'm imagining the most trivial case where I only get to insert identities or something like that. You know, to be very nonsensical.
Right, we're supposing that the
you have this measure of
in the setup.
Yeah.
Right, in the setup we said we're imagining putting Haar-random. So the theorem is a statement about an architecture, and then we said the architecture. With the architecture, you can implement any unitary in a particular set, U of A, and imagine plucking one of those unitaries at random. By at random, we mean, according to our setup, if you choose the gates Haar-randomly, then the unitary will have a complexity that obeys this linear lower bound. But that setup can be generalized. So when you pluck this unitary at random from the set of all implementable unitaries, you don't actually have to choose the gates Haar-randomly. You just need to choose the gates according to any measure that is absolutely continuous with respect to the Haar measure. So if according to the Haar measure, there's a 0 probability of choosing gate X, maybe I shouldn't have said X, gate G, then according to any allowable measure, also there should be a probability 0 of choosing gate G.
I see.
So there was also a question that I said I would defer to the end of the talk about why the bound holds for an exponentially long time. So maybe I can explain a little more fully now. So let's see. So we said that the really important concept here is the accessible dimension, and the accessible dimension is a measure of the number of degrees of freedom that you need to describe this set of all unitaries implemented with the architecture of interest. And so basically we want to show that the accessible dimension grows in time. And we ask, well, how long can this accessible dimension grow in time? And the accessible dimension is, like, suppose that originally I have this circuit, I'm slotting some gates into the circuit, that gets mapped to a unitary. Well, suppose that I change my gates ever so slightly. How much does the unitary change? That's really what we're interested in. And we can show that quantity, in how many directions does this set of implementable unitaries change. We can show that grows because as you add more and more gates onto your circuit for an exponentially long time, because at first, if you have just a short circuit, then you can sort of, your circuit can map a Pauli operator to a whole bunch of Pauli operators, but not quite all of them. And then if you add more gates, you allow yourself more freedom. Yeah, a longer circuit can realize more of the Pauli strings. And then if you add more gates, then your circuit can realize more of the Pauli strings. And how long can we go on, realizing more and more of the Pauli strings? Well, there are only 4 to the n minus 1 non-trivial Pauli strings. So that's a bound on how long we can keep up this pattern.
Okay, thank you. And maybe final question here, but there was some interest in your quantum steampunk book that we mentioned at the beginning. Would you care to share a little bit more about that with us and what that is and when the book's coming out and so on?
Sure. This is a book that was written for the general public, but it's supposed to be fun for scientists too, and especially IBM physicists. As I mentioned when we were just talking one-on-one, IBM Quantum actually shows up in the book. A few years ago, I visited IBM Watson and got a lab tour, and so that appears in the book. So keep an eye out if you are someone at IBM. Now, the book is about quantum information theoretic thermodynamics, which is what I do. The idea is that thermodynamics was developed a long time ago, during the 1800s, to describe big classical systems like steam engines. But today we have very small systems. We're also interested in far from equilibrium systems outside of conventional thermodynamics. We're interested in quantum systems like superconducting qubits that have to be cooled to very low temperatures. So concepts from conventional thermodynamics need to be reimagined for the 21st century. And we've had quantum statistical mechanics for a long time, but thermodynamics really has a different flavor. It's really operational. Like information theory, quantum information theory itself. We think about agents performing tasks. In the case of thermodynamics, those tasks could be extracting work or charging batteries or refrigerating. So there's this wonderful worldwide community of quantum thermodynamicists who at first are re-envisioning thermodynamics and also discovering how we could use quantum resources to achieve thermodynamic tasks in a way that we can't with just classical resources. Similarly, how we can use quantum phenomena to solve computational problems, certain computational problems, much more quickly than we can with classical systems. And we're also, one thing that I really enjoy doing and some of my colleagues enjoy doing is taking this toolkit of quantum thermodynamics and taking it over into high energy physics and condensed matter and atomic molecular and optical physics and seeing how we can re-envision the problems there using tools like resource theories. And I see this field as having the aesthetic of steampunk. The steampunk is a genre of literature, art, and film. It combines old Victorian settings from the 1800s with futuristic technologies like time machines and automata and dirigibles. So there's this wonderful sense of adventure and romance and exploration. And quantum thermodynamics is a very similar fusion of two different eras. Thermodynamics was developed during the 1800s, the steampunk era, and yet it extends to the futuristic technologies of quantum computers. So I see the field as really sharing the spirit of steampunk, and I try to get that across in the book. So it was a lot of fun to write, and I hope it's fun to read. It's available for pre-ordering from all the usual sources and being published in under 2 months, March 22nd.
Thank you, Nicole, for writing the book. I'm excited. I can I guess share that I pre-ordered it, I think July 15, 2021. So avidly waiting for it,
I
and
appreciate it.
I think see that I'm looking forward to it. Maybe we'll have a book reading one day, and I think,
Great.
folks, with that we can, seeing as we're about 10 minutes over. Maybe if you'd like to add any final words before we close.
Thanks so much for all the questions and all the input. The back and forth has been fantastic. And thanks again for your time. It's really been a pleasure to be here.
Thank you, Nicole. Thank you, folks, for tuning in. This talk will stay live. This talk will stay recorded, so you can go back and rewatch it. I hope you enjoyed Nicole's presentation as much as I did. And with that, we will see you next Friday at noon Eastern Time.